Well, yeah, it's related. Okay, so we're going to have our new formulas today, and I'll talk about what they mean. So we're going to do magnetism. Now, the thing with magnetism is that it's different from electricity because with electricity, you can have a separate positive charge and a negative charge that's separate. And what direction do field lines go with charges?
Towards the positive. Away from positive.
Away from the positive.
You're pretending you're a positive particle.
Charges would be affected.
Right. Okay. Now, what happens if I take this negative charge away?
They just go out.
They just go out, but I still have a perfectly good electric field coming out of here. So I can have just a positive charge. Now let's say this entire thing, the whole thing goes away, and I have just a negative charge. What do the field lines look like?
They all go in.
They just go in. Okay, but with magnetism, there's no such thing as a magnetic monopole, meaning you can't have just a north pole or just a south pole. Anytime you have a magnet, you have to have both a north pole and a south pole. As far as we know, I don't think that there's any theory that says it has to be this way. It just is. Okay, so anytime you have a magnet, you have a north pole and you have a south pole. And if I break this magnet in half and make two magnets, say, okay, I'm going to get that north pole by itself. No, what happens is you end up with two magnets, one with the north pole and a south pole, and the other one with the north pole and a south pole. But we do have magnetic fields, and magnetic fields go from the north pole to the south pole. So all field lines start on a north pole and end at a south pole. Now, depending on the shape of your magnet, you'll have different field lines, but this is how they look. And you can see those in videos, or if you do it yourself, if you get little iron filings, little shavings of iron.
And they have that at all museums.
Yeah, they do. And you have magnets, and you kind of sprinkle the iron filings on. You can see that they take the shape on the field lines. Now, I'm assuming everybody has, an understanding of what a magnet is, because you don't have to know all the details of how it works, but you've used them, so you know what we're talking about. And we're going to see how electricity and magnetism are related. So one thing that's going to be important here is that we're going to have to start dealing with 3 dimensions because of the way that electric fields and magnetic fields interact. So we're going to learn some new notation here. Maybe. Okay, and our new notation is going to be 3-dimensional notation. So when we are denoting a magnetic field, this is actually true for any field, but we'll be using it mostly for magnetic fields, but we could use it for electric fields. When we draw little dots, this is indicating a magnetic field . That's an F. That says field.
Sure.
Coming out of the page. And that's actually generally what we say, out of the page, out of the board, and now out of the screen. It's just, so it's coming out that dimension, or from that dimension. And if instead we draw little X's, it's going into the page. And the way to remember that is it's supposed to be kind of like an arrow. And so the points are showing the arrow tips, they're coming towards you, and the X's are the arrow feathers, so it's going into the page. I think I'll erase rather than making a new page because it's kind of fun. And again, that I did that for a magnetic field, but that's the notation for any kind of field. Okay, so here is our first big formula. Should we change colors for that?
Yeah.
Yeah, I think so. Let's see. Color. I don't know which one of these it is. It seems like it'd be color editor. Yeah, that seems good. So F equals QVB sine theta. Okay, so what this is the force, and it's important to keep track of our formulas and what they are, because they're going to be forces on moving charges or forces caused by currents. And this one is important because this one is the force on a moving charge due to a magnetic field. I'm getting a little better at this. No, field seems to throw me for a loop.
Cats often sound like
Mr. Morton? No, it's just Mr. Morton. It's because of his ear surgery. He can't really hear, and so he yells really loud so that he can hear himself. And yeah.
Yeah.
That's mean.
No, it isn't. It's true.
It's true.
Yeah, because what happened was he had surgery and it rerouted because he was having all kinds of problems with his ears. So now he just has, and he had his cone. He just has tiny little holes below his ears are just for show. They don't really do anything. But he was very vain and he said, I need my ears. But it was funny because when they sewed them back, one of them was a little bit crooked. Okay, so anyway. So this is the force on a moving charge due to a magnetic field. Now, one thing that's important to notice here is there's this sine theta actually makes a difference, because what is the sine of 0 degrees? 0. And what's the sine of 180 degrees? Also 0. So let's say this is the direction of our magnetic field. And we throw a charge in here. Plus or minus doesn't matter. I think it needs to be a different color. Can you see it?
Positive.
Yeah, I was
'cause
going to
it's
say
good.
positive charge because the charge lines.
Okay, so we have a positive charge here, and let's say it's moving in this direction. What is the force on this charge due to this magnetic field? Yeah, it's 0, because the angle between the velocity and the magnetic field is 0 degrees, and so the force is 0.
That's a lowercase v.
It's a lowercase v stands for velocity, right?
Right. Just gotta make sure it's not voltage for some reason.
Yeah, well, you never know. Okay, now let's say our positive charge, that's supposed to be a straight line in this direction. Let's say our positive charge is moving in this direction. What's the force on it due to the magnetic field? Also 0. Okay, so in what direction should it be moving in order to have the maximum force? Perpendicular. So if it's moving, that's up, either up or down, you'll have the maximum force, and then sine theta will be 1. And in a lot of your problems, that's going to be the case, so you don't have to worry about the sine theta. It'll say it's moving perpendicularly to a magnetic field. And so in order to have any kind of force, it has to have a component that's perpendicular to a magnetic field. Another thing that often throws people for a loop, and it seems really easy when you look at the formula, and right now you'll say, well, duh, but then later on there'll be a problem will come up, and you'll be, I'm not sure. What is the force on this charge? Well, I guess it'll be a new charge. What is the force on this charge while it's just sitting there? What's V?
Oh, V is
Zero.
0.
V is 0. Yeah, so it's 0. So a stationary charge in a magnetic field doesn't care that it's in a magnetic field. It has 0 force on it. Okay,
What's V?
I am going to pause for a moment. I can remember how. Really excellent question. So we kind of need to know what B is. So I didn't define that. B is the strength of the magnetic field I cannot write field. In units called Teslas.
After the better scientist.
Okay, and while I'm paused, why don't y'all figure out what the equivalent, what a Tesla is, or what an equivalent form of a Tesla is.